اوكي، بسم الله الرحمن الرحيم. رب اشرح لي صدري ويسر لي امري واحلل عقدة من لساني يفقهوا قولي. Today, inshallah, we are going to talk about the colligated properties. Warning outcome 10. Okay, Bismillah ar-Rahman ar-Rahim. For the colligated properties, warning outcome 10, colligated properties of the solutions, it is the properties depend on the amount of the solute which dissolve in the solvent. And when you have four different properties, which are the vapor pressure, VB, elevation in the boiling point, depression and freezing point, and the osmatic pressure. But before talking about these properties, we must return back to determine the ability of the ionic salt to dissolve in the different salts, especially in the water, since the water is one from the polar solvents that we deal with it to make a dissolution for the more or the thousand of the substances, especially the salts. Okay, if we return back to the solubility chart, which determines the ability of the salts to dissolve, we'll find that the salt especially depend on the anion, the negative part that come from the acid. So if we look to the fluoride anion, we'll find all the salts of the fluorine can soluble in the water, but except we'll find exceptional some the magnesium fluoride, calcium fluoride, strontium fluoride, barium fluoride, manganese fluoride, and lead fluoride. All of them are not dissolved in the water, and we find slightly soluble in the water like the aluminum. So we can return to this chart as an example. So all the nitrate salts are soluble in the water. We can return to this chart to determine the ability of the salts to dissolve in the water. Now we are going to talk about the first property, talking about the vapor pressure. If we put an amount of the water inside a closed container and we close this top, like if we bring the round bottom flask like in front of you, and we will start to boil it, we'll find firstly when they reach the boiling point, the amount of the vapor it will increase in this area. This is represented the vapor pressure. If we transfer this round bottom flask to the cool place, we'll find the condensation start taking place. So firstly, the rate of evaporation is high, then in the second case, we'll find the rate of condensation will be increased till we reach the equilibrium state. The equilibrium state taking place when the rate of evaporation equals the rate of condensation. This is called the chemical equilibrium. But we talk about the pressure that causes by the vapor. The vapor causes the vapor pressure. What's meant by the vapor pressure? It represents the pressure of the vapor effect on the surface of the liquid. So, if we start to compare between the two substances, like the pure solvent substance, there is no salt with it, like the pure water or distilled water, and the vapor pressure of the solutions. So firstly, you'll find what? You'll find if we put the distilled water in the closed container and start to heating it, we'll find the vapor pressure will be increased. Since no solid particle attached with the water molecule, so we'll find the vapor pressure will be increased for the pure solvent. But in case of the solutions, we'll find the solid particle represented by the red color attached with the particle of the solvent. So we decrease the vapor pressure. So from these two experiments, we'll find that the general conclusion, the vapor pressure of solvent, pure solvent, greater than the vapor pressure of the solution. Amount of the vapor that formed from the pure solvent greater than the amount of the vapor that formed from the solution. This property will affect the another colligated properties like the elevation in the boiling point. If we talk about the elevation in boiling point, If we make in the solutions, saturated solution 100 gram of the water as a standard or as an rubric, you will find to forming the saturated solutions you must dissolve the substance in 100 gram of the water. يبقى أنا عشان أكون saturated solution لازم dissolve the substance in 100 gram of the water. طيب. We bring the substance and we compare if we dissolve the salt in 100 gram of the water in front of the temperature. Firstly, we will find this is line by dots to represent the normal atmospheric pressure. We will find the pure solvent, its boil at 100 degrees. And the salty solutions, it boil at the TB. What's meant by the TB? It is the elevation in the boiling point. If we compare between the vapor pressure of the pure solvent and the vapor pressure of the solution, we will find the vapor pressure lower than vapor pressure of the solution, lower than the vapor pressure of the pure solvent. But the boiling point of the solutions is greater than the boiling point of the pure solvent. So vapor pressure of the pure solvent is greater than the vapor pressure of the solutions, but the boiling point of the pure solvent is less than the boiling point of the solutions. The rule which controls the boiling point is called delta TB equal I dot KB dot molality. Elevation in boiling point I represent the vent Huff factor. Molality represent number of moles of solute divided the mass of solvent in kilogram. If we talk about the number of moles equal mass of the substance divided in molar mass. Okay, to determine which is salted the higher in the boiling point, determine the identity of the salt. If the salt is the ionic, we must return to the higher in the number of the ions moles is the higher in the boiling point. This is represented the return back to the vent Huff factor. We are going to talk about the example for this especially. But for the covalent compound, we must talk that the higher in the boiling point is the higher in the molar mass. As an example, if we compare between the sodium chloride and the calcium phosphate, return back to the number of moles of ions which produced from each one in the aqueous solution, we will find the sodium chloride it produces 1 mole of the sodium ion and 1 mole of the chlorine ion. So the total number of the moles in the aqueous solution represents the 2 moles of ions. But if we return back to the calcium phosphate, we will find the calcium phosphate give to us in the aqueous solution 3 mole of the calcium ions and 1 mole of phosphate ions. So the total number will be 4 moles of ions. So the higher in the boiling point in this case, if they have the same molarity, in case they have same molality, and number of moles. You will find that the calcium phosphate is higher in the boiling point since it reduced the 4 moles of the iron in the aqueous solutions. But in the case of the covalent compound, whose is higher in the boiling point, the urea or the glucose sugar? If we return back to the molar mass of each one, you will find the urea, it represents 60 gram per mole, but the glucose sugar, it represents 180 gram per mole, since we'll find the higher in the molar mass, it will be the sugar, so it's higher in the boiling point. Note, non-electrolytic material vent Hope factor for them equal 1. So the I equal 1. Okay, let's talk about an example according to the vapor pressures, one from the difficult questions from the test bank. Bismillah ar-Rahman ar-Rahim. Okay. Okay. Which one of the following solutions has the lowest boiling point? 0.15 molar from the sodium chloride, 0.1 molar from the magnesium bromide, 0.15 molar from molal from the barium nitrate, or 0.20 molal from the glucose sugar, or 0.1 molal from the iron nitrate. Firstly, the delta TB equal I times vent Hall times the KB represent the boiling point constant and may represent the molality. So we must return back to add it. Bismillah. Boiling point constant. Boiling point constant. Okay. Firstly, 0.1 molar from sodium chloride. If we return to determine the vent Hall factor for the sodium chloride, we'll find the sodium chloride in the aqueous solution of the water. It gave to us 1 mole of the sodium ion and 1 mole of the chlorine ion. So the vent Hall factor, it will be 2. Delta TB equal I times delta TB equal I times KB times M. We'll find the 2 times 0.1, it will be 0.2. If you know that the KB, it will be constant for all of them. KB, it will be constant. So, in the case of the magnesium bromide giving to us 3 moles of iron, so it will be 3 times 0.15. Let's talk about it in the calculator. Okay. So in this case, we'll find 3 times 0.15 equals 0.45, 0.45. In the another case, 0.40 degrees Celsius. And this is the degrees Celsius. Return back to the third one. For the barium nitrate, the Ventol factor delta B equal I times molality. So giving to us 1 for the, it will be represented as 3 in this case. Bismillah. So delta T equal I times Lm. So it will be 3 times 0.15 else equals 0.45. For the glucose sugar, represents Bismillah ar-Rahman ar-Rahim 0.2 C2 H6O2. So it will be Ventol factor, it will be 1. So I times M will represent 0.2 degrees Celsius. The third one or the last one will find that the iron nitrate gave it to us the 4 moles of the ions. So delta PB, it will be 4 times 0.1 equals 0.4 degrees Celsius. Delta TB, it will be the lowest for the C2H6O2, so it will have the lowest boiling point. So according to the rule, we will find we can solve this problem. Okay, return back. Bismillah ar-Rahman ar-Rahim. Depression in the freezing point. Freezing point we'll find firstly, when you're talking about the solubility of the substance in 100 grams of the water, you will find firstly the substance, the pure solvent, it's boil at 100 degree and the freeze at 0 degree. In this case, we will find the substance will be in the phase of the liquid substance. But if we're increasing the temperature, then 100 degrees Celsius, we will find the substance it enter in the phase, it will be in the gaseous state. But if we're decreasing the temperature, then 0 degree we will find in the phase of the solid. We return back to the graph. We will find firstly TF represent the freezing point of the solutions, freezing point for the solutions, TV boiling point of solution, 100 represent the boiling point of pure water, of pure solvent, 0 degrees Celsius represent the freezing point of pure solvent. To return back to the graph, you will find it. It will be this graph represented the previous graph, but by regular shape. We'll find this the melting curve, and we'll find this it will be in the phase of the vapor, this is in the phase of the solid, this is in the phase of the liquid. So for the freezing point, if we talk about the substance for the vapor pressure is increased for a pure solvent. If we compare between the pure solvent and the solutions, Bismillah, pure solvent, solution. If we talk for the vapor pressure, we will find the vapor pressure of the pure solvent is high, but the vapor pressure of the solution is decreased. For the boiling point, we will find the boiling point for the pure solvent is low, while the boiling point of the solution is high. For the freezing point, we will find the freezing point for the pure solvent is high, then the freezing point of the solutions. So the freezing point of the solution, it will be decreased, then the freezing point of the pure solvent. So in this case, vapor pressure of the pure solvent higher than, with another color, freezing point of the pure solvent higher than, but the boiling point of the pure solvent lower than, freezing point of the pure solvent higher than the freezing point of the solutions. As an application, the freezing point, we'll find that it could be in the cold countries. They spared the salts at the two sides of the route to lowering the freezing point of the solutions. That causes the formation of the ice to take a long period of time. To return to delta TF equal I times KF times molality. In this case, we will find that the value of the Kf sometimes it will be 1.86 Kf times the molality. So if we're talking about the freezing point, expected freezing point for the sodium chloride, the Van 't Hoff factor, it will be I equal 2, since we have a sodium, 1 mole of the sodium ion and 1 mole of the chlorine, and Kf, it will be 1.86 in case in the molality equal 1. So the expected temperatures, depression temperature, it will be 2 times negative 1.86. It will depression taking place by negative 3.72 degrees Celsius. Freezing point of the solvent is greater than the freezing point of the solutions. Okay, the last property we are going to talk about it, talking about the osmatic pressure. But before talking about the osmatic pressure, we can return back to solve a problem on the freezing point. Bismillah. Bismillah. Okay, this problem. Thyroxine is an important hormone that controls the rate of the metabolism in the body. Can be isolated from the thyroid gland. If 0.45 gram of the thyroxine is dissolved in the 10 gram of the benzene, the freezing point of the solutions could be measured as 5.144 degrees Celsius. The pure solvent freeze at 5.444 degrees Celsius has the value for the molar freezing point depressions constant. Kf of 5.12 degrees Celsius per molar. What is the approximate molar mass of the thyroxine? Firstly, we must determine the depression of freezing point. Depression of freezing point can be calculated. Delta Tf represent the Tf for pure solvent subtracted the Tf for the solution. Tf for the pure solvent is benzene 5.444. Subtract the boiling point, our freezing point for the solution, it will be 5.144. So it equals 0.3 degrees Celsius. If we return back to the rule, we'll find Van 't Hoff in this case I equal 1. Since it is the non-electrolyte substance. Okay, so Kf times the molality. Molality can be calculated from number of moles, which represent the mass, divided the molar mass, divided the mass of the solvent in the kilogram. So the mass of the substance is 0.455, divided the molar mass, divided 10 gram of the pure solvent, divided the 1000 to calculate it in the kilogram. So we'll find 0.3 equal 5.12 for the Kf divided the summary of this. It will be 45.5 divided the molar mass. So the molar mass, it will be 5.12 times 45.5 divided 0.3. It will be equal 776.53, which represent 3/7. So the answer, it will be P. Okay. Return back to the osmatic pressure. Bismillah. Osmatic pressure and the reverse osmosis. Osmatic pressure by equal MRT may be multiplied in the Vent-Hoff factor. This is osmatic pressure Vent-Hoff factor. This is the molar concentration constant gas law, constant of the gas. This is the temperature in Kelvin. This is represent if we inhabit the U-shaped tube. And we put semi-permeable membrane between the two openings, semi-permeable membrane. One of its corner on one of its side we put the solution, and in the other side we put the solvent. So the direction of the pure solvent of pure solvent. We note that the pure solvent start to move toward the direction of pure solvent pass through membrane. And not return back. But if we apply reverse osmosis through test, we enforce the pure solvent to return back to the solution. Again. So in this case, when all the particles of the pure solvent pass We will effect by the piston in the liquid, force it to return back the liquid to return back to another direction. Reverse osmosis applied. Okay, for the problem of the reverse osmosis, we are going to talk about that. Let's take an example for the problems that come in the case of the reverse osmosis. Bismillah. Okay, firstly, a 0.1 molar of the solution of the solute X in the benzene display an osmatic pressure is giving that the formula by equal 0.1 RT, which one of the following most likely to be the case? X exists in the benzene as X represents the solute, okay? X existed in the benzene as X2, X exists in the benzene dissociated in the two particles. طبعا دي مش معقولة عشان هو ده non-polar solvent. The solution strongly deviates from the ideal behavior. Okay, firstly, we return back to the biosmatic pressure. Okay, if we return to the pi equal I times molality, or molarity times the R times the T, but we'll find the IM in this case represents 0.1. Van 't Hoff factor for non-polar solvents will represent 1. So I in this case it will be 0.1 divided in 0.1 divided the molarity, we will find the molarity is 0.2. It represents 0.5. Since the I less than 1, associations not dissociation taking place. يعني particles بتاعت السوليوت بتميل ان هي في اللحظه دي try to attach to each other and not dissociate it. So we'll find the association not dissociations taking place, so the X's become X2. The particles associate with each other. Okay, another problem. Calculate the molarity of the solutions that containing the Kc, question number 91 in the Zomdel test bank, of the water whose osmotic pressure at 21.6 degrees Celsius is 125 Kelvin. Assume that it is complete dissociated salt. Okay. Firstly, when we have the KCl or NaCl, NaCl, KCl, it will be dissociated into K positive and chlorine negative, okay, in aqueous solution. So Van 't Hoff factor, it will be 2. If we apply in the rule, firstly we must convert the terror to atmospheric pressure, ATM. So when I have 125, the H1 ATM equal 760 terror. If when I have an 125 cross multiplication, so when I have 1 times 125 divided 760 will be represent 0.1645. R equal the constant 0.0821. Later dot ATM dot M mole -1 Kelvin -1. But for the temperature we must convert temperature to the degree Kelvin. So 380 38.9 plus 273 equals 312.09. Return back to calculate the molarity in this case. The molarity will be pi divided IRT 0.1645 divided 0.0821 times 312.09 times 2 when 12 factor, it will be 0.00321. Okay. This file, inshallah, it will pass to all of you. It included the hard and difficult questions, difficult and moderate questions on the test bank in just learning outcome. If we return back to talk about the colloidal solutions, now we are going to talk about the colloidal. Bismillah. Now let's stop with the chair. Okay. Okay, Bismillah.